Hello. Welcome to Cubesat Constellations, Millimeter Wave and Terahertz System Applications for Remote Sensing of Precipitation with Stephen Rising. I'm Mike Hamilton, your host for this IEEE Microwave Theory and Technique Society webcast, which is sponsored by National Instruments. Before we start, I'll mention a few housekeeping items. First, this presentation will be archived. A recording should be posted approximately 24 hours after we finish the presentation. We will send all registrants an email when the archived webinar goes up so you can revisit it or share it with your colleagues. Second, we encourage questions. We will answer them after the talk, but you can submit them at any time during the discussion. Enter them in the Q&A box on the left side of the webcast window, and please don't forget to click Submit. Third, some words about the interface. You can enlarge slides by clicking on the green rectangle at the top right of the slide area. If you're listening over your computer speakers, you can adjust the volume in the media player area at the upper left of the screen. Remember, you may also need to adjust your system's master volume. Also, the icons at the bottom of the webinar window include a file folder. This links to a resource page where you should be able to download PDF copies of the slides. Now let's introduce our speaker. Dr. Stephen C. Rising has been full professor in electrical and computer engineering at Colorado State University, CSU, since 2011, where he served as associate professor from 2004 to 2011. Prior to joining CSU, he was assistant professor at the University of Massachusetts in Amherst from 1998 to 2004, where he received tenure. Dr. Rising received a PhD degree in electrical engineering from Stanford University in 1998, where he was supported by a NASA Earth Systems Science Fellowship. Dr. Rising's research interests span a broad range of disciplines, including microwave remote sensing of the Earth's atmosphere and oceans, Earth science measurements from nanosatellites and CubeSats, passive remote sensing systems from microwave to submillimeter wave frequencies, approximately 18 to 670 gigahertz, and low-noise monolithic microwave integrated circuit, or MMIC, design and packaging. He has been principal investigator of 14 grants over the past 15 years from NASA, the NASA Science Foundation, NSF, the Department of Defense, Office of Naval Research Labs, INPO's Integrated Program Office, Ball Aerospace and Technologies, and the European Space Agency. Dr. Rising recently received the 2015 George T. Abel Outstanding Research Faculty Award from the College of Engineering at CSU. So now it's my pleasure to turn the virtual podium over to Dr. Steve Rising for CubeSat Constellations, Millimeter Wave and Terahertz System Applications for Remote Sensing of Precipitation. Stephen?
Thank you very much, Mike. Thank you for your generous introduction. And I wish good day to everyone. I'm talking, as Mike said, about constellations of CubeSats, and in particular what can be done with millimeter wave and terahertz systems applied to remote sensing of precipitation and Earth observation. So first I'd like to acknowledge that this work, the part that we've done, is sponsored by NASA's Earth Science Technology Office. That's run by George Komar, and program managers in this area are Bob Bauer, Parminder Guman, and Keith Murray. This work would not be possible without many collaborators, including Jet Propulsion Laboratory in Pasadena, California. The group that we're most closely working with is led by Todd Geyer, and key co-investigator is Pekka Kangaslahti. We're also working with Blue Canyon Technologies as a spacecraft bus provider. They're in Boulder, Colorado, about 1 hour drive from where I am in Fort Collins, Colorado. And we're working closely with Northrop Grumman, with the group led by Bill Deal for MIMIC design and LNA production. So I'll speak more about that soon. So what we're showing here is the CubeSat deployment from the International Space Station. So these CubeSats are ejected from nanoracks deployers, and this is part of the robot arm of the Japanese experiment module. And so the CubeSats are ejected, as you see here, at 1 meter per second, and they quickly move away from the space station. And then you get a view here of the entire large solar array on the space station. You see the CubeSats just below the robot arm in white. and then they're drifting toward Earth, and they're separating. So CubeSats, so then they're on their own after they're deployed. And so they have to have everything except for, typically they do not use propulsion, but they have solar panels, they have deployable solar arrays in some instances, they have electric power system, guidance, navigation and control, onboard computers, GPS, inertial navigation units, and as well as communications to ground and sometimes to other satellites to downlink the data and uplink commands from the ground. So so what is a CubeSat? Well, a CubeSat was defined in about 1999 by Stanford University and Cal Poly as a standard platform, a standard size for deploying small payloads into space for easier access to space. And so they're based on this dimension of U, which is basically a 10-centimeter cube, or 4 inches for imperial units, and each 1U, so we can build up a CubeSat from sets of 1U. So that doesn't mean that each 1U is an independent satellite. For instance, in the lower right, you see 3U CubeSats right there. And so they're built up of 3 1U units, and the dimensions of those are 34, of the 3Us are 34 by 10 by 10 centimeters, and up to 4 kilograms. And so these are the standards that allow these CubeSats to be deployed as secondary payloads on other missions. And so there's plenty of room in the launchers typically for something like this, and then they're put together in a P-pod, like peas in a pod. So that stands for Polypico Satellite Orbital Deployer, which is again a standard to be able to get these CubeSats into space. And we're using the example from the International Space Station. There are many other deployment mechanisms, as we'll see. However, then when we go greater than in size than 3U, for instance, a 6U, so we've doubled the other dimensions. It would be like putting these two you see on the right together side by side, and so they'd have a width of, height of 34 centimeters, a width of 20 centimeters, and a depth of 10 centimeters. So in imperial units, that's about 12 by 8 by 4 inches. And so the mass there is allowed to go up to 12 kilograms. And so the benefits are greater resources, obviously greater solar panel area to charge the batteries, the potential for increased capacity in a number of ways, as well as redundancy of satellite-to-ground communications. There's just enough resources to do things in terms of mass and volume. And you can see more on NASA's website with these exciting photos. So NASA also provides for U.S. educational institutions, nonprofits, and NASA centers, provides what's called the CubeSat Launch Initiative. It's also been called the Educational Launch of Nanosatellites. But the CSLI, as I'll refer to it, provides opportunities for small payloads to fly on launchers that are already planned. And so as you see in the lower right, there are plenty of different launch providers, and one of them there is the fifth column is the International Space Station, through commercial resupply service. So you see out of the total, that's 16 out of a total of 98. So there are many other, and there's also the NASA's Earth Science Division, led by Mike Freilich, has initiated the Venture Class Launch Services, and that's shown in 31 there in the lower right. To date, 49 CubeSats have launched through this initiative, and 119 missions have been selected, ongoing into the future. And it's about half education, half research, and about 2/3 technology demonstration. So the National Academies in Washington, D.C., National Academy of Sciences, Engineering, and Medicine is its formal name. Now, they convened a committee on achieving science goals with CubeSats. And as you see, Thomas Zurbuchen, professor at University of Michigan, is the chair. There are members from Caltech, Google, MIT, Johns Hopkins, Lockheed Martin, and so on. So this is a prestigious group. And they convened a number of panels, and they issued the report just a couple of months ago about how to achieve science with CubeSats. And so you see on the top right somebody loading a P-pod deployer, And then these CubeSats are down in the lower right of the fairing of the Delta II rocket. So you see they don't take up much volume. And so the keys are meeting the standards that have been developed for CubeSats, as well as generally no propulsion and, do no harm, right, to the primary payload. That's paramount. So results of this study include looking at, using the data compiled by Professor Swartwout at St. Louis University, and looking at the increase in over time of CubeSat missions. And so you see there's a dramatic increase in 2013 and again in 2014. And this is mainly due to a commercial provider, Planet Labs, for an imaging CubeSat constellation. But there's a whole variety of purposes to launch CubeSats. Technology demonstration is shown in purple, science in red, imaging in blue. So you see there's a bulk of 2014 and 2015 is Earth imaging, education in yellow, and communications in green. So we can also break it down by the sponsor within the U.S. Universities are shown in yellow. There's National Science Foundation, NASA, military, commercial, and other civilian. So the report looked also at the global distribution of CubeSat missions, which has lowered the barrier to space, especially for a number of countries that either participated, say European countries that participated through ESA and EUMETSAT, and have a space presence, but they want to have their own space presence and increase what their universities can do and their as well as their space initiatives. And so we see that U.S. has greater than 3/4 to date, but there have been many countries involved, as you see by this color scale, and you can see more on the National Academy's website. So here's an example of a mission that's very important to NASA. NASA has launched the Earth Venture line of missions, and they've funded instruments and so on. But this is a very important mission that's going to launch this November. It's slated just before Thanksgiving in the U.S. and about 68 days from now. So here's one of the satellites on the top left. That's their logo on the middle left, and the constellation is shown on the right, where blue are GPS receivers. So they're in middle Earth orbit. They're already up there. And the 8 satellites are clustered around the equator in yellow. The 8 satellites will be deployed from one rocket, and then they'll spread out in longitude and have a tropics and near tropics focused orbit. And so they'll be able to measure that's why we have the GPS constellation and GNSS in general. They'll be able to receive direct signals from the GPS satellites as well as those reflected from the ocean surface. And so those frequencies at, L1 is at 1.575 gigahertz, can propagate through the storms and get significant reflections from the ocean surface, indicating the roughness of the ocean surface and the ability to measure wind. And they're looking at other products as well on soil moisture on land and tsunami detection from undersea earthquakes. So that's going to be an important mission inspired by CubeSat technology, and basically each of those satellites is 25 kilograms and uses uses a navigation system, guidance, navigation, and control built by Blue Canyon Technologies in Boulder, Colorado. And so I want to turn the focus to a constellation of 6U CubeSats, and I'll call them 6U class satellites, because we want to turn the focus toward doing science and not just allowing easy access to space for students. That's part of the CubeSat venture, but they're really maturing and becoming more reliable so that that we can do science with CubeSats. And we're specifically doing Earth science here. And so it's part of, we proposed a 5-satellite constellation, 5 6U CubeSats in the same orbital plane to measure, to use millimeter wave radiometers to look inside clouds and precipitation to measure how it changes with time. And this would be the first such ability to measure temporal signatures of precipitation. So it was proposed in 2013 to EVI, Earth Venture Instrument 2 call, and selected for in-space technology demonstration to be managed by NASA's Earth Science Technology Office. That's ESTO that I mentioned before. And so the demonstration began 1 year ago. It's going to be ready for launch in less than a year from now. So it's a very fast time scale. It's again compatible with graduate education on the time scale of degrees. So you can go, PhD student could go from a proposal all the way through to data analysis. And also new technology can be infused in the CubeSat missions. So this was manifested by CSLI that I mentioned before. And the mission is called ELENA. That's from Educational Launch of Nanosatellites, ELENA 23, to go up in the first half of 2018 by a commercial resupply service. So, for instance, SpaceX and Orbital ATK. And to the International Space Station for deployment using nanoracks that I showed you in the first slide. So what is Tempest going to do? Tempest, the entire constellation, deploys 5 satellites. If we deploy them roughly at the same time, using nanoracks, they'll be in the same orbital plane. But then what we need to do is to separate them. And so without propulsion, we can still separate them in orbit. We can turn them, since we have very fine attitude control, we can turn them so that a larger portion is facing into the wind. They'll be then lowered in altitude one by one. And with the lower altitude gives a shorter orbital period, and so then they move ahead one by one. And so we can control the distance they are apart. So the Tempest mission is using 5 identical 6U class satellites with a 5-channel millimeter wave radiometer. You see the frequencies there in the lower left, flying 5 minutes apart. And what will that do? In the upper right, you can see a simulation, which I'll show in more detail in the next slide, where 5 minutes apart we can observe we can strongly detect the onset of precipitation in a cloud. So what will this do? This will be the first global observations of the time evolution of cloud processes and precipitation. It will help not only weather forecasting, but also climate models, to improve climate models through our understanding of how clouds develop to rainfall, and how that happens around the world. So the information from ground radars is not enough to be able to measure this temporal development. And we look at the transition to precipitation and the impact on Earth's energy balance, and look at the global water cycle. So in a little bit more detail, we show a simulation. The first row shows the development of the storm. The second row shows infrared. So infrared is available from geosynchronous satellites that you've seen on the Weather Channel and other media, where you get 5 to 10 minute samples with, from geostationary satellites. So you can always observe it. But the infrared cannot penetrate into the cloud, and there's no microwave or millimeter wave receivers available in geosynchronous orbit. So if we have a 165 gigahertz in the third row, there's a large change in the brightness temperature at the onset of precipitation. And so this has been verified both by models and measurements, and we see many tens of Kelvin. So on the scale on the right, we're far above the noise level. And so the spatial resolution is shown in 25-kilometer circles. So the reason to do this is to improve climate models. And for instance, my colleague Graham Stevens, who was a distinguished professor at Colorado State University, is now at the Jet Propulsion Lab in Pasadena. He and his many co-authors have looked at global climate models, and they've looked at the sensitivity to droplet sizes. You see in the center, red is 6 microns or micrometers, 8 micrometers is green, and 11 is blue. And so we show that this is the droplet size that needs to be achieved before rainfall starts. And so the global temperature is very sensitive to that. So also in addition to this, if you see in the second panel, you see a step function. In all of these, you see a negative step function where we're going from a higher level, like at 280 in the second panel, down to 250. You see a large step function at the onset of precipitation for all of our frequencies from 90 to approximately 180 gigahertz. And we see the asterisks in the third panel show the time sampling. So if we sample at that time of a storm, then we can see not only that step function, but also the recovery. The recovery depends on things like the collection of water on ice crystals, which is very important for the effects on the climate system of how much of the clouds, how long the clouds remain after they've rained out. And so we can also compare our measurements to W-band radar observations from CloudSat at 94 gigahertz or ESA's EarthCare mission. So when we also validated this the simulations by measuring from aircraft. This is JPL's high-altitude mimic sounding radiometer called HAMSR, and it flies on the Global Hawk at 20 kilometers, which is roughly 60,000 feet, and it observes all kinds of precipitation, including specializing in hurricanes. And then on the next slide, on one of the experiments sponsored by NOAA and NASA off the West Coast, we had the pilot of the ER2. Okay, so this was a piloted aircraft. The Global Hawk was an unpiloted aircraft shown in the previous slide. But the pilot was able to fly over about every 5 minutes over this storm. And we didn't know it from the visible and infrared imagery, but there were actually two cores there. And the two cores are shown here. One of them, A, was in the lower panel on the right, was growing and precipitation was starting. We can see by the decrease. And in B, the cloud was observed already precipitating, and then it recovered. As you see, the brightness temperature increased at the end in green on the top right. So zooming out again to the entire mission, a Tempest mission of 1 year in duration can make more than 3 million temporal observations of precipitation, so measuring the multiple samples as precipitation develops. And that's for precipitation of greater than 1 millimeter per hour as detected by the AMSR-E radiometer on the Aqua satellite in NASA's A-Train. So in the lower panel, so that's shown in the upper panel, the 3 million observations, including 100,000 deep convection events. And the lower panel shows the overlap with the Global Precipitation Mission, NASA's GPM, a signature mission that's been flying since 2014, following on the tropical rainfall measuring mission that started in 1997 and lasted nearly 18 years. And so if Tempest is deployed from the International Space Station at a 400-kilometer altitude, 51-degree inclination orbit, it will overlap many times GPM. And that will provide more information because GPM is a large satellite and it has the ability to measure at a lot more frequencies as well as the active radar at 2 frequencies. So the motivation here is to demonstrate our technology for the Tempest demonstration. That's the D is for demonstration. The motivation is to demonstrate our technology for 6U class nanosatellites. It's particular to reduce the risk. So we have a lot of processes to reduce the risk, to demonstrate the reliable Earth science measurements for future constellations. And how are we going to do that? We're going to demonstrate that these orbital drag maneuvers are feasible, that we can control the altitude very carefully by, you see in the lower right, one of the satellites. And so the 6U is in the bottom there, and you see 2 sets of solar panels. And so the satellite will be reoriented to provide maximum drag, bring it down 100 meters in altitude, and then put it back to low drag configuration. And so that will be achieved by measuring with GPS. And then to demonstrate the instrument, the millimeter wave radiometers, we demonstrate precision intercalibration, comparing with Global Precipitation Mission, the passive part, the radiometer part, which is microwave imager, and microwave humidity sensor, MHS, on both U.S. and European satellites, which has 4 of them in orbit. And that's very high precision. Also, we are providing the first in-space technology demonstration of a millimeter wave radiometer with an indium phosphide hemp low noise amplifier front end. So that's our collaboration with Northrop Grumman, and that's for Earth science measurements. That'll be the first indium phosphide hemp LNA for Earth science measurements in space. And we're a partnership among CSU, Colorado State University, JPL, Jet Propulsion Laboratory, and Blue Canyon Technologies. So JPL is providing the instrument, CSU is doing the validation, and Blue Canyon Technology is providing the spacecraft, instrument integration, operations. So we're raising what NASA calls the technology readiness level of the radiometer instrument from 6 to 7 on a scale of up to 9, and we were selected by the CSLI, manifested for the first half of 2018 for 3 months of on-orbit demonstration. So here's the initial sensor design. I'm not going to spend much time on it, just to show you that it's evolved from the initial design from 91 to 183 gigahertz to the current design, which is a mature configuration. So we've redesigned the mechanical parts of the instrument to be much easier to control its temperature. And so as you see in the left figure, you see the reflector that rotates at 30 rotations per minute. So every 2 seconds, we observe the Earth scene. We look to the right to get cold space for the cosmic background radiation at 2.7 Kelvin, and we look up above the reflector antenna at the ambient blackbody calibration load. So basically, radiometers are extremely sensitive microwave, well, in this case, millimeter wave receivers, and they need to be calibrated very often. And so we have absolute calibration here with cold space view and an end-to-end calibration every 2 seconds. And so we view the Earth scene over plus or minus 45 degrees from nadir, as you see the cross-track scan there in the left figure. And from 400-kilometer orbit, that would be 825-kilometer swath width. And every scan we view cold space in blue in the middle figure and calibration target in red, giving data like on the right figure. So the instrument requirements are that the noise temperature, receiver noise temperature, needs to be better than 600 Kelvin at the lower 3 frequencies and better than 750 Kelvin at the 2 higher frequencies. Our bandwidths are 4 gigahertz and 2 gigahertz at the lower and higher frequencies respectively. Our spatial resolution, this is the projection of the half-power beamwidth to the ground is 13 kilometers at the highest frequency, millimeter wave frequency, and 25 kilometers at the lowest frequency. So the technical resources in the 6U class satellite look very good. We have large margins of 30% for mass. We allocated 4 kilograms. We have 20%, almost 20% margin for power. We allocated 6.5 watts. This is continuously operating power for the radiometer. Then continuous data rate is just under 10 kilobits per second. That's a 20% margin. And we have redundant methods of communication to ground. Then the precision of the radiometer is 0.7 Kelvin. We measure the power. We scale the power to Kelvin. And the accuracy is 3.5 Kelvin, mostly dominated by antenna pattern correction errors that can be improved on orbit. So we show the margins, actual margin here in the third column, and then the CDR, we passed our CDR at the end of July. Critical design review. So the technology the heritage of the technology is based on a project led by Sharmila Padmanabhan, my former student at JPL, and this was funded internally at JPL. It's called the Microwave Atmospheric Sounder on CubeSat, and you see it in the fuselage at the top center next to RainCube. RainCube is a 6U CubeSat radar, which is planned to be deployed on the same ISS mission as ours, as the Tempest demonstrator. But this is MASC, which was demonstrated in 2 aircraft campaigns, qualified in thermal vacuum testing last year. And one of the campaigns is shown here in airborne, and this is the airborne deployment in Olympex, which was in the winter season last winter, and they did extensive comparisons between the data in the lower center and the lower left for the satellite radiometer. So I'll talk a little more about technology now. The Northrop Grumman has worked with JPL for quite a number of years with their indium phosphide hemp process for low noise amplifiers. And this is a 35 nanometer process. This was published by Pekka Kangaslahti of JPL and Bill Deal and many co-authors at IMS of 2012 in Montreal. And what this showed was the third bullet is the record low noise temperature of 300 to 350 Kelvin from 140 to 190 gigahertz. So that happens to be a frequency range that's important for atmospheric sensing due to the water vapor absorption line at 183.3 gigahertz. And so the millimeter wave direct detection receiver is what we use in Tempest-D and planned for Tempest as well. And so there's a number of just packages shown here. On the top, there's a top left, there are the LNAs concatenated with a filter, and then there's a power divider assembly, and of course we use bandpass filters at the RF frequency because we're using direct detection from 90 to 183 gigahertz. And these prototypes have been successfully tested. Can't go into too much detail, but the block diagram here shows the 4 channels together. They're in WR5 waveguide coming out of the antenna. The feed horn is a dual frequency feed horn with a WR5 output at the top and a WR10 output at the bottom for the 89 gigahertz. And so the key here is this direct detection allows us to eliminate the local oscillator and mixer and have lower power of 5 watts continuous operation. And then here is showing that we've measured the prototype bandpass filters. All 4 of them is shown in the photo. And we've achieved the center frequencies and bandwidths well within the error allocations. So Tempest-D is a technology demonstration in space to reduce the risk and demonstrate NASA the capability to do future NASA Earth science measurements. So the technology demonstration focusing on the orbital drag maneuvers that I mentioned, as well as the intercalibration of millimeter wave radiometers with existing spaceborne assets. So it is a development cycle of 2 years to be ready for launch in 2017, and we're manifested for a launch in early 2018. Okay, so I'd like to briefly take a look at instrument development that we're doing. This is a lower technology readiness level, but it's also funded by the Earth Science Technology Office to extend to terahertz. And so this is a tropospheric water and cloud ice, but it's motivated by science, of course. So in the upper troposphere, the upper area of the atmosphere where our weather happens, then you just have 2 phases of water. You have water vapor and ice. And so the current microwave sensors mostly measure at single local times, say 6 a.m. and 6 p.m., for instance. And there are a variety of reasons for doing that, but we're interested in a variety of local times to see how it affects the diurnal cycle of diurnal heating from the sun and cooling at night, affects water vapor profiles, and affects the ice particle size distribution. So the ice particle size distribution is very important and something that's undermeasured right now. It's very important for uncertainties in climate models, as well as the connection to aerosols. So the simple explanation is that aerosols make the water droplets smaller. We tend to have, for a given amount of water available in the cloud, there are smaller water droplets or smaller ice crystals higher in the clouds that constitutes the first indirect effect of aerosols, which may be from pollution. And polluted clouds then are less likely to generate rainfall because the raindrops don't get to the size to fall. And then they hang around longer, and they have brighter albedo that reflects the sun than clean clouds do. So down in the lower right, there's a dependence on whether we have aerosols in the cloud or that it's a clean cloud. There's a dependence of how the amount of ice relates to the amount of rainfall. And so we are designing a radiometer instrument to measure ice cloud particle size. So there's basically a gap between what infrared can measure at smaller than 100 microns, micrometers, and what CloudSat radar can measure just because of its frequency choice of greater than 1 millimeters. So in that decade gap, factor of 10 gap in particle size, we sub-millimeter wave frequencies up to terahertz match very well. And so this figure shows the differential scattering, the difference scattering due to ice particles. So basically, ice particles scatter away the signal that you would measure, but not all of it, just some of it. And so we can measure that difference in terms of Kelvin right here on the right. And so we're designing an instrument to do that, to do ice cloud particle sizing as well as water vapor sounding. So water vapor sounding is based on the pressure broadening of absorption lines. So the resonances get wider when there are get wider in frequency, so like a lower Q filter, when there are more collisions with the atmosphere, with other particles in the atmosphere besides water vapor, and that happens closer to the ground. And so you see, as you go away, so 0 gigahertz in these figures is right on the absorption line, and then as you move away from the absorption line, below it in this case, like a few gigahertz, then we move down in altitude. And so we have a very, a quite sensitive way to measure water vapor, and then we can measure temperature profiles using 118 gigahertz channels as well. So we're combining all of these measurements in a sub-millimeter wave and terahertz radiometer. And so I won't go into detail, but basically this diagram shows we have various areas of responsibility between Colorado State University, Jet Propulsion Laboratory, and Northrop Grumman Corporation. We're putting them all together in one 6U CubeSat. And so some of the technology has been already demonstrated for the GeoStar project, again ESTO funded, as well as the HAMMER, which I'll talk about in a minute. These airborne instruments have shown receiver modules in 118, have demonstrated them, and they work very well. And the receiver modules in 183, so so-called MIMRAM, the lower left. And lower right, there's a analog spectrometer designed in ASIC very well by Professor Razavi at UCLA. So then the performance has been very good. We have demonstrated specifically on the high-frequency airborne microwave and millimeter wave radiometer, HAMMR or HAMMER. We've demonstrated temperature and humidity sounding near 118 and 183 gigahertz. You see my postdoc and students in the lower center. And so in addition to other frequency channels, part of it is the temperature and humidity sounders that we showed in the last slide. So the TWICE instrument fits in the 6U class spacecraft. We combine the 3 frequency bands in one quasi-optical system. So they range from 118 gigahertz in the lower end to 670 gigahertz in the high end. And this scans at a constant, it's a conical scan. So it views the Earth at a constant angle. It also views cold sky, reflector, and ambient calibrator. This is shown here in preliminary design. And then the optics design is in more detail. We base this on Planck, the radio astronomy instrument that flew very successfully for a number of years. And there's a primary reflector and a secondary reflector. The secondary reflector is oversized. So basically it's larger than is needed for the focal length of these feed horns shown here. And so we can fit more feed horns into the focal plane in that way. And we have a number of design criteria that we do for designing the receivers. So the Northrop Grumman has focused on development of MMICs, and JPL has designed some of the MMICs as well for the 25 nanometer indium phosphide hemp process. This was developed under other larger funding sources, and very synergistically has worked very well for NASA. So on the left, we see 670 gigahertz MMIC LNA, and they have prototyped the direct detection receiver, and the final integrated receiver is shown in CAD at the bottom left there. And then they're supporting in addition to MMIC design and chip fabrication and chip testing, they're designing packaging for, or implementing packaging for 230 to 390 gigahertz channels. So the TWICE 670 gigahertz receiver is shown here. So we start on the left with the feed horn. The feed horn was designed by JPL, and it was validated, and the antenna patterns were measured and compared with theory, compared very well. And then that has a WR 1.5 output, very small. into the 25 nanometer indium phosphide HEMT LNAs operating at 670 gigahertz. These were validated in package. So we've finished the first the first wafer run, and we measured 10 dB gain. It was lower than expected, and there's a second run which is in process now, and we should have measurements before the end of the year, as well as putting dicing chips and putting them in packages. We expect several dB higher gain. Also, 11 dB noise figure has been achieved with a LNAs tested in package using the Y-factor method. And then the bandpass filters were again developed for another program and adapted to this one. And so we have direct detection at 670 gigahertz. The spec is 20 gigahertz. Right now, 30 gigahertz has been measured for bandwidth. But we can also do the atmospheric measurement with a wider frequency range. Then Virginia Diodes has developed the detectors, and we have a validated, tested design that works at 670 gigahertz. Video amplifier was designed by JPL and will be repeated by Northrop Grumman. So we are developing a tropospheric water and cloud ice, a 6U CubeSat instrument for global measurements of cloud ice and water vapor profiles in the upper part of the atmosphere, so in storms. And they're needed to improve global climate modeling of cloud processes, so including both climate predictions and the knowledge of their uncertainty. So basically, one of the key inputs, they can do, there are plenty of global models that have been run, and they can look at the sensitivity to the uncertainties. Okay, so sort of looking at PDFs and, changing those PDFs, and they see that the fact that they don't know the cloud processes well in terms of the cloud ice particle sizes, that has a big effect on climate simulations. So that's why cloud ice particle sizing is needed, and the sensitivity. So we can't measure aerosols directly, but other instruments, other complementary instruments, and plenty of scientists are working on aerosols and air pollution and how it affects clouds, specifically how it affects clouds and precipitation. And so these are called the indirect effects of aerosols. And we're interested in global measurements throughout the cycle of day and night. So TWICE is performing measurements at 15 frequencies from 118 gigahertz to 670 gigahertz for cloud ice particle size information, as well as profiling of temperature and water vapor. And the conical scanning will give us a fixed polarization basis as opposed to cross-track scanning, and will enable external calibration, end-to-end calibration using a cold sky at 2.7 Kelvin and an ambient target at a well-measured temperature, and basically a black body. So TWICE will meet the size, weight, and power criteria for 6U class satellite. So with that, I'd like to thank you very much for your attention. Thank many students who worked with me, several postdocs, and of course my excellent collaborators at Jet Propulsion Lab, Northrop Grumman Corporation in Redondo Beach, and Blue Canyon Technologies in Boulder, Colorado. And of course, we thank the program managers and sponsors at the NASA Earth Science Technology Office, as well as the Earth Science Division Flight Program. Thank you.
Great. Thank you very much, Stephen. That was an excellent presentation. Really provided a lot of insight into all the details that goes on with putting these systems together. So now it's time for our question and answer session, which will be more of an interactive portion of this webinar. And before we start, please remember that you can still submit questions through the Q&A panel. Okay, so here is our first question. And this refers back to slide 14. What difference were you getting from the various frequency bands? Go back to slide 14.
Okay, finding that slide. There we go. Thank you. Thank you. That's a great question. So the different frequency bands relate to they penetrate to different depths in the cloud. So if we look back at this slide, you're seeing slide 11. So the frequencies that are closer to the 183 gigahertz absorption line measure higher in the cloud, and the others measure lower in the cloud. And so specifically 165 and 89 gigahertz can penetrate very well, particularly 89 gigahertz penetrate deeper into the cloud. And so they measure different parts of the altitude profile of that cloud and how they develop differently.
Okay, great.
And
we've got
so they provide, sorry, Mike, they provide orthogonal information on various processes of the cloud, like the ice evolution in time.
Great. Okay. So we have several questions here about kind of digging a little bit deeper into the technology, and more specifically, there are questions about the source side and the filtering side. So I was wondering if you could fill in some more details about the source side, for example.
Sure, I'd be happy to do that. So I'll just bring up this slide about the block diagram. So basically, the source of our information is natural emission. So it's Planck blackbody radiation. That's basically, so say you look at a cloud-free scene. You're seeing blackbody radiation, just like when you measure a person or a vehicle with an infrared camera, night vision goggles, you see their natural radiation against the background. And so when you fly from a clear sky case and flying over a cloud, then you see a big change in terms of the natural emission. And then in a cloud, in the higher parts, particularly when we have ice, at these frequencies we have scattering. And so the scattering changes the amplitude of the signal. It decreases the amplitude of the signal because that's scattered away. Just like when you're looking at the sky, optically you're seeing scattered light when you're not looking directly at the sun. So the scattered light then decreases, so you're able to look at processes in the cloud. And so the second was the filtering. Is that the second part of the question?
Yeah, specifically, one of the questions is what technology is used for the 670 gigahertz bandpass filters?
Yes, those are waveguide. Yeah,
but there are several here about filters, and it would be just clarifying some of the details of that.
Sure, those are waveguide-based filters, and they have a number of stages. So I don't have the detailed information right here, so I can provide a little more information offline. But they have been, they've been thoroughly tested and validated to be able to provide the frequency responses we need to be able to do direct detection at 90 through 180 gigahertz and at 670 gigahertz as well.
Okay, great. We have a question. How do you manage to keep the weight down for the terahertz horn feeds? What material is used?
Oh, this is a very small horn. For the terahertz horn, that's a very small horn, and you can make it in aluminum and gold plated or brass, and so the weight, it's so small that the weight is really not a concern. If you look at, let's look back at slide 40. We see the size of the 670 gigahertz horn aperture. See, it's so small that we've integrated it into the. So this, let's see, this slide would show it a little better. On the lower left, the CAD drawing there with sort of a brown assembly. Okay, so the gold assembly in the lower left, again, the gold assembly is shown, blocks that we connect together using waveguides, and then we see the antenna out there on the left. That's the antenna aperture. It's a feed horn, and so it's integrated right into the assembly in the CAD drawing at the lower part, and so it's so small that we can integrate it right into the same block, and then we can minimize the waveguide losses between each component by having it in a single integrated receiver. Go ahead, Mike.
Great. Okay. Yeah. No, that makes a lot of sense. And we have another question. Similarly, just in the same vein, but maybe a little bit larger scope outside of even the millimeter wave side of things. But what is the scope of research and antenna design for CubeSats? Is there anything that you can comment on from your perspective?
Well, there's a very large scope. That's a very good question. I know Professor Yahya Ramatsami at UCLA edited a special issue of the IEEE Antennas and Propagation Society magazine based on that. So that's a very broad scope. So antenna miniaturization is definitely of interest. Antennas for communications from CubeSats is also an interesting topic. UHF is used a lot for communications, and which is relatively simpler antennas, but there have been communication systems proposed and beginning testing from S-band, X-band, and then optical communications as well, from satellites to ground. So the sensor research, as I showed, the optical setup here with the primary and secondary reflectors, and then we have the feed horns. So I can give them a little more information on feed horns offline. And so basically the needs are simulation capabilities in terms of educationally, simulation capabilities like HFSS and so on, as well as various computational electromagnetics to measure the patterns both in the near field, as you see here, and the far field. Back to you, Mike.
Okay. So back to some more of the core microwave system details. What is the detection bandwidth of the diodes? Obviously, it's dependent on the frequency range, but also how does that relate to the seemingly narrow video bandwidth?
Yes, that's good. So the diodes, detector diodes, like here shown in the green background from VDI, those are power detectors. They're functioning as square law power detectors, and they have a broad bandwidth, and it really depends on how you match them. So you use microwave matching techniques to allow them to operate well at the frequency range you're interested in. So I would say they're significantly broader than this 20 gigahertz band that we're interested in measuring here. Then the output of them is an envelope detected signal, and so it has a low bandwidth.
Okay. We actually have a follow-up question to your comment about Professor Ramasami's special issue in A&P. Do you know which issue that might be? It sounds like there may be some folks who are interested to know that.
Well, I don't have that off the top of my head, but I'm sure we can find out. We can look at IEEE Explore.
Yep. Be easy enough. Yeah. Let's see. Here's a question about what happens to the CubeSats at the end of the 3-month mission. Always a mysterious question.
Oh, that's a very good question. Yes. So for instance, Blue Canyon Technologies, that's designing the bus and all of the things that I mentioned, like communications, integrating communications receivers, power control, guidance, navigation, and control, charging the battery, and so on, and integrating it all together. They have designed everything for up to a 3-year lifetime. So this particular technology demonstration mission focuses on 3 months. of demonstration, and that's what's required. But the lifetime of everything we're building is certainly, more like a 3-year lifetime. Okay, so BCT is designing for a 3-year lifetime. The radiometer measurements radiometers have been demonstrated in space for 15 years, something like that. And so obviously there are some new processes here. But so then the other question is just orbital drag on CubeSats, and that tends to that may limit their lifetime to a couple of years. It depends on the orbit, depends on the drag coefficient. It even depends on the solar cycle of how dense the atmosphere is. And so we've had detailed modelers that basically handle the orbital dynamics to Mars and Jupiter and Saturn for JPL. And so they've looked at the modeling, and we're definitely good for a year and a half. So if we could, if we can get additional funds, we'd like to continue to operate it. But the initial demonstration, our requirement is to do it in 3 months. Go ahead.
Great, sure. Okay, and so we'll take just this one last question, but thanks for answering everything so far. And listeners, you can still submit a question, and we can answer those offline. So the last question here is, what are your thoughts on making these hyperspectral systems on CubeSats?
Oh, I think it's great. Yeah, I think they're complementary to the microwave and millimeter wave systems. They can be done. Okay, so I assume they're referring to hyperspectral infrared. They could be referring to hyperspectral microwave too, but typically the word is applied to infrared, and infrared's limited to basically clear sky measurements, but they can get higher resolution profiles of temperature and humidity in the atmosphere, and they're very useful and very complementary. And there are a number of projects that are funded by NASA ESTO which exploit that capability as well. Thanks.
And you think it would fit on a CubeSat?
Yes, they are funded through the INVEST program of ESTO to fit on a 6U CubeSat.
Oh, great. Okay. Very good. Okay. Well, thanks a lot, Stephen. Okay, ladies and gentlemen, I'm afraid we're out of time. We do still have a handful of questions here, and the presenter will follow up with those questions offline. As we said earlier in the session, earlier in this webinar, the session will be archived at mtt.org, and all registrants will get an email reminder with a website address when it is available. For attendees that would like to receive PDH credits, please follow the link in the webcast view and use the code that is provided on the last slide of the presentation that is shown right now. And once again, I'd like to thank Professor Rising for an excellent presentation. Our thanks also go out to National Instruments, who is the sponsor for this webinar. And special thanks to our audience for joining us today. We hope you found today's event valuable and that you will return for future IEEE Microwave Theory and Technique Society webcasts. Thank you and have a good day.